Look up into the night sky. What do you see? Tiny points of light scattered like diamond dust on black velvet. For thousands of years, humans have gazed at these stars, finding patterns, telling stories, and navigating vast oceans. We have always known they were special, but we are only just beginning to understand how truly incredible they are. These stars are not just distant fires burning in the void. They are the universe's great storytellers, holding the secrets of cosmic history within their fiery hearts. Each star is a time capsule, a chapter in a grand narrative that stretches back to the very beginning of everything. The light from these stars travels incredible distances to reach our eyes. Some of it has been traveling for so long that when you look at a star, you are actually looking into the past. For most of human history, our understanding of the stars was limited to what we could see with our own eyes. We saw them as eternal and unchanging, fixed points in the heavens. The invention of the telescope changed everything. Suddenly, the universe expanded. The faint, blurry patch of the Milky Way resolved into countless individual stars. To truly understand the stars, we needed to do more than just look at their light. We needed to break it apart. This is where a technique called spectroscopy comes in. When astronomers do this with starlight, they see something amazing. The spectrum is crossed by dark lines like a barcode. Each element absorbs light at specific wavelengths, creating a unique pattern. This stellar barcode is a chemical signature. By reading this cosmic barcode, astronomers can figure out exactly what a star is made of with incredible precision. We learned that stars are mostly made of hydrogen and helium, the two lightest elements created in the Big Bang. But we also discovered that they contain tiny traces of other, heavier elements. As astronomers studied the chemical barcodes of more and more stars, a fascinating pattern began to emerge. Not all stars are created equal. They do not all have the same chemical makeup. This discovery led to one of the most powerful ideas in modern astronomy, the concept of stellar populations. Instead of being one big happy family, stars belong to different generations. Scientists have classified stars into three main groups, known as Population 1, Population 2, and Population 3. Our own Sun is a Population 1 star. It is relatively young and rich in heavy elements. These heavy elements are what astronomers, in their own quirky language, call metals. In astronomy, a metal is any element that is not hydrogen or helium. Population 1 stars, like our Sun, are found in the spiral arms of galaxies like our own Milky Way, where star formation is active and ongoing. They are the newest generation, the cosmic children born into a universe already enriched by their ancestors. Understanding metallicity is kind of like discovering the secret ingredient in a recipe that's been handed down through generations. So, imagine for a moment that the universe is this giant kitchen. The Big Bang was the moment someone stocked the pantry for the very first time. They only put two ingredients on the shelves, giant bags of hydrogen flour and big tubs of helium butter. With just these two basic ingredients, you could make a simple kind of cosmic bread, the very first stars. But honestly, it would be a very plain, very simple loaf. Deep within a star's core, hydrogen atoms are fused together to make helium. In more massive stars, the process keeps going. Helium atoms are fused to create carbon. Carbon and helium make oxygen. The star becomes a cosmic spice rack, creating new, more complex ingredients that just weren't there at the beginning. These new ingredients are the astronomical metals. A supernova is like a cosmic chef flinging open the oven door and scattering the contents of the mixing bowl all across the kitchen. The explosion blasts all those newly forged metals out into space. Let's take a moment to imagine what that very early universe was like, before the first stars had a chance to cook up any metals. Picture a cosmos, filled with nothing but vast, dark clouds of hydrogen and helium gas. It was a simple, almost featureless place. There were no planets, no asteroids, no dust. There was no carbon for life, no oxygen to breathe, no silicon for rocks. The universe was a blank canvas, waiting for the first artists, the first stars, to add some color. Forming a star requires gravity to pull a cloud of gas together until it becomes hot and dense enough to ignite nuclear fusion. In today's universe, this process is helped along by metals, but in the early metal-free universe, this helping hand just didn't exist. Without any metals to help the gas cool down, it was much harder for gravity to do its job. The only way to form a star was to go big. Really, really big. The first stars, the theoretical population 3 stars, must have been colossal, hundreds of times more massive than our own sun. We journey to the cosmic dawn, a period roughly 200 to 400 million years after the Big Bang. For millions of years, the universe had been a dark, expanding sea of neutral gas, an epoch astronomers call the Cosmic Dark Ages. In that instant, the first stars ignited, and the Cosmic Dark Ages came to a spectacular end. The first light blazed across the universe. These were the population 3 stars, the long-lost ancestors of every star that followed. Their birth was not a gentle flicker, but a roaring inferno, tearing through the darkness that had shrouded the cosmos for hundreds of millions of years. What would these first stars have been like? They were true titans of the cosmos, behemoths of unimaginable scale and power. Imagine a star so large that if you placed it where our sun is, it would swallow the orbits of the inner planets. Because of their immense mass, these stars would have been incredibly hot and luminous. Their surface temperatures would have reached over 100,000 degrees Celsius, many times hotter than our sun's relatively cool 5,500 degrees. Their composition was, by definition, pristine. They were forged from the raw materials of the Big Bang, meaning they were made of almost pure hydrogen and helium. Their metallicity was practically zero. There is a fundamental rule in the lives of stars. The more massive a star is, the shorter its life will be. It's a classic case of live fast, die young. Think of it like comparing a tiny scooter to a monster truck. The truck has a much bigger fuel tank, but its massive engine consumes fuel so quickly that it will run empty long before the scooter does. The population 3 stars were the ultimate cosmic monster trucks. While a star like our sun will happily chug along for about 10 billion years, the population 3 giants would have exhausted their entire fuel supply in a cosmic blink of an eye. Their intense, energetic light had a dramatic effect on their surroundings. The light from these stars was predominantly in the ultraviolet part of the spectrum. This high-energy radiation acted like a cosmic blowtorch, blasting apart the neutral hydrogen atoms in the surrounding gas clouds. This process, known as reionization, transformed the universe from a cold, neutral state back into the hot, ionized plasma it had been just after the Big Bang. The first stars began to carve out huge bubbles of transparent ionized gas in the opaque fog of the Dark Ages. The brief, violent lives of the population 3 stars were therefore not just an isolated event. They were the trigger for a universe-wide transformation, the first step in making the cosmos a more hospitable place for future generations of stars and galaxies. And the true legacy of the population 3 stars was not what they did during their short lives, but what they did in their spectacular deaths. Inside their intensely hot and dense cores, they were the universe's first alchemists, the first cosmic forges. Under the crushing weight of their own gravity, these stars fused hydrogen into helium. Once the hydrogen in the core was used up, the star would contract further, reaching even higher temperatures and pressures. In these primordial stellar furnaces, the first atoms of carbon were forged. Then came oxygen, neon, magnesium, and silicon. For the first time, the universe was creating elements essential for building planets and for life as we know it. This process of forging new elements continued until the star's core was filled with iron. Iron is a special kind of nuclear ash. Fusing it does not release energy, but instead consumes it. When a massive star's core becomes iron, its energy source is cut off. In a fraction of a second, gravity wins a catastrophic victory. The core collapses under its own immense weight, and the outer layers of the star come crashing down onto it, rebounding in a titanic explosion known as a supernova. These first supernovae were the most powerful explosions the universe had seen since the Big Bang itself. The blast hurled all these newly created elements, from carbon to uranium, far out into interstellar space. The alchemists had not only created gold, they had distributed it across the cosmos. The death of the first stars was the birth of a new kind of universe. The metals they forged and scattered were the seeds from which all future complexity would grow. These heavy elements drifted through space, mixing with the vast, untouched clouds of hydrogen and helium. When the next generation of stars began to form, they were born from this enriched material. This new, slightly metallic gas behaved very differently from the pristine gas that formed the population 3 stars. The presence of elements like carbon and oxygen acted as an efficient coolant. As the new gas clouds began to collapse under gravity, these heavy elements radiated heat away far more effectively than hydrogen and helium ever could. This allowed the clouds to cool down faster, lose pressure, and fragment into much smaller clumps. This meant that the next generation of stars, the population 2 stars, did not have to be so mind-bogglingly massive. The universe could now form a wider variety of stars, including many that were smaller and longer-lived. This was a game-changing development. The ability to form smaller, more stable stars meant that the universe could sustain star formation over much longer timescales. Instead of burning out in a few million years, these new stars could last for billions of years. Where can we find these venerable population 2 stars today? We must look for them in the most ancient parts of our own galaxy. Most spectacularly, they are found in tightly packed communities known as globular clusters. A globular cluster is a breathtaking sight. It is a dense, spherical swarm containing hundreds of thousands, sometimes millions of ancient stars, all gravitationally bound together. These clusters are like stellar cities, orbiting the main disk of our galaxy. When we analyze the light from these stars, their chemical barcodes reveal their true nature. They are profoundly metal-poor, containing only a tiny fraction of the heavy elements found in our Sun. They are the quintessential population 2 objects. Studying these ancient survivors gives us a direct window into the past. It's like an archaeologist finding a perfectly preserved settlement from a long-lost civilization. By analyzing the chemistry of these stars, we can measure the level of enrichment in the early universe. The fact that these stars are still around is a testament to their longevity. Unlike their massive population 3 ancestors, many population 2 stars were small enough to have lifespans longer than the current age of the universe. They have been shining steadily for over 13 billion years, silent witnesses to the entire history of our galaxy's formation. They are the quiet, enduring elders of our galactic family, and their light carries the tale of a younger, simpler cosmos. After billions of years of cosmic alchemy, the universe was finally ready for its next great creation. The continuous cycle of starbirth and death, driven by the population 2 stars, had gradually enriched the interstellar medium with a substantial inventory of heavy elements. This chemical abundance set the stage for the arrival of the youngest and most chemically complex generation of stars, population 1. These are the modern stars, the metal-rich inhabitants of the universe, and they include the most important star in our lives, our very own Sun. Population 1 stars are defined by their high metallicity. Whereas their population 2 ancestors were metal-poor, population 1 stars are metal-rich. However, the fraction of heavy elements in a star like our Sun is significantly higher, maybe 10 to 100 times greater than in a typical population 2 star. You find these stellar newcomers in the most active and dynamic parts of a galaxy. They reside primarily in the spiral arms of galaxies like the Milky Way, the bright, bustling boulevards of cosmic cities. These are the regions where vast clouds of gas and dust are still plentiful, and star formation is an ongoing, vibrant process. Unlike the ancient population 2 stars, which are scattered in the galactic halo and bulge, population 1 stars are part of the current scene. The high metallicity of these stars influences their characteristics, but the most significant consequence of their metal-rich nature is not what it does to the stars themselves, but what it enables to form around them. The abundance of heavy elements in the disk of gas and dust that surrounds a young population 1 star is the crucial ingredient needed for one of the most exciting developments in the cosmos, the formation of planets. Let us zoom in on our own local story, which began about 4.6 billion years ago. In a quiet, unremarkable spiral arm of the Milky Way galaxy, a vast, cold cloud of gas and dust began to collapse under its own gravity. This was not a pristine cloud of hydrogen and helium, nor was it the slightly enriched gas that formed the population 2 stars. This cloud was the product of billions of years of galactic recycling. It was rich in the metals forged and scattered by countless supernova explosions over cosmic eons. As this metal-rich cloud contracted, it started to spin faster and flatten into a disk, just like a spinning ball of pizza dough. At the center of this swirling disk, matter became increasingly compressed and heated. The gravitational pressure mounted, and the temperature at the core soared past the critical 10 million degree threshold. Nuclear fusion ignited, and a new star was born, our Sun. As a population 1 star, it was born with a healthy inheritance of heavy elements, about 2% of its mass consisting of metals. This chemical signature is its birth certificate, telling us it is a child of a long line of stellar ancestors. Surrounding the young glowing star was the leftover material, a massive rotating protoplanetary disk of gas and dust. This disk was a cosmic construction site, brimming with potential. It contained all the elements of the periodic table, from the abundant hydrogen and helium gas to the tiny but crucial grains of silicates, iron compounds, and frozen water ice. The formation of planets within the protoplanetary disk was a story of cosmic sorting dictated by temperature. Close to the young hot sun, conditions were scorching. This temperature gradient created a frost line or snow line in the young solar system. Inside this line, only rock and metal could clump together. Because rock and metal made up only a tiny fraction of the disk's total mass, there was not much raw material to work with. The planets that formed here were destined to be relatively small, dense, and rocky. This is the origin story of Mercury, Venus, Earth, and Mars. They are the direct result of having enough heavy elements to form solid worlds in the hot inner region of the solar system. Beyond the frost line, the situation was completely different. Here it was cold enough for water ice to form solid particles. This meant there was vastly more solid material available for building planets. The cores of planets in this outer region could grow much larger, much faster. These massive cores, rich in ice and rock, quickly became so gravitationally dominant that they began to pull in huge amounts of surrounding hydrogen and helium gas. This process created the gas giants, Jupiter and Saturn. This clear division between small rocky inner planets and large gassy outer planets is a direct consequence of metallicity. The existence of a world like Earth, with its iron core and silicate mantle, is inextricably linked to the fact that our Sun is a metal-rich population 1 star. The importance of high metallicity goes beyond just building planets. It is fundamental to the possibility of life as we know it. The iron in our blood that carries oxygen, the calcium in our bones that gives us structure, and the phosphorus in our DNA that carries our genetic code. All of these are metals in the astronomical sense. They are elements forged in the hearts of long-dead stars and incorporated into the cloud from which our solar system formed. A star system born around a very low metallicity population 2 star would be a poor candidate for life. Even if it could form planets, which is unlikely, those planets would be severely deprived of the essential elements for biology. Imagine a world with no carbon, no oxygen, no nitrogen, no phosphorus. It would be a sterile, geologically simple place, incapable of developing the rich chemical complexity that life requires. Furthermore, metallicity influences a planet's ability to sustain a stable environment over geological timescales. A planet needs a certain size and density to retain an atmosphere and to maintain a hot, active core. This active core, rich in iron and nickel, generates a magnetic field that shields the planet's surface and atmosphere from the harsh solar wind and cosmic radiation. So when we search for potentially habitable exoplanets around other stars, one of the first things astronomers look at is the metallicity of the host star. A star with a metallicity similar to our Sun is considered a much more promising target for finding rocky, Earth-like worlds than a metal-poor star. Our connection to the stars is not just poetic, it is literal and profound. We are made of the ashes of ancestral stars, living on a rocky planet that could only form because our Sun belongs to the metal-rich generation. Our journey through cosmic time reveals a universe that is not static but is constantly evolving, driven by the lives and deaths of its stars. We began in a simple, almost featureless cosmos, made only of hydrogen and helium. It was the first generation of stars, the colossal and short-lived population 3, that initiated the Great Transformation. From their ashes rose the second generation, the ancient and metal-poor population 2 stars. This brings us to our own cosmic era, the age of the metal-rich population 1 stars like our Sun. We are the beneficiaries of this immense cosmic inheritance. The high metallicity of our star is the reason we have a solar system with rocky planets, and the reason our own world possesses the essential ingredients for life. The iron in our blood, the calcium in our bones, and the carbon that forms the basis of our biology were all forged in the hearts of stars that died long before the Earth was born. The story of Metallicity is a grand, unbroken chain of cause and effect, linking the biggest explosions in the universe to the smallest atoms within our bodies. Thus, when we gaze up at the night sky, we are looking at more than just distant points of light. We are seeing our own cosmic family tree, a story of stellar generations written in the language of light and chemistry. It is a profound and humbling narrative of connection, demonstrating that in the universe, nothing is wasted. The death of one star provides the building blocks for the next, and ultimately, for worlds and for us. We are not separate from the cosmos, looking in from the outside. We are a part of it, made from it, and a direct result of its magnificent unfolding story. We are quite literally stardust,